In this video, you will learn how to solve some Hardy-Weinberg problems. But before that, let us know what a Hardy-Weinberg equilibrium is. The Hardy-Weinberg equilibrium is a principle stating that the genetic variation in a population will remain constant from one generation to the next in the absence of disturbing factors. Right, it predicts how gene frequencies will be inherited from generation to generation given a specific set of assumptions. Or it states that allele and genotype frequencies in a population will remain constant from generation to generation in the absence of other evolutionary influences. So the Hardy-Weinberg equilibrium has an equation or formula. If there are only two alleles for a trait in a population, then p squared plus 2pq plus q squared equals 1, and p plus q equals 1, where p here is the dominant allele frequency, q is the frequency of the recessive allele, and then p squared is the frequency of the homozygous dominant genotype. Then 2pq is the frequency of heterozygous genotype. And then q squared is the frequency of homozygous recessive genotype. So p here is dominant to q. Let's solve some sample problems here. A population of cats can be either black or white. The black allele, denoted as big B, has complete dominance over the white allele, denoted as small b. Given a population of 1,000 cats, 840 black and 160 white, determine the allele frequency, the frequency of individuals per genotype, and number of individuals per genotype. Now, to solve this problem, we just have to determine all of those variables I've previously discussed, which are p, q, p squared, 2pq, and q squared. I've already previously defined each of the variables. So the first thing we do here is to find the frequency of white cats, which is the homozygous recessive genotype, as they have only one genotype, which is denoted as 2 small b's. And then black cats can have either the genotype big B, denoted as big B and small b, or the genotype BB. Alright, this is for the black cats. Okay, it has two genotypes, therefore the frequency here cannot be directly determined. Now, to solve for the frequency of individuals, we just have to divide the individuals, the number of individuals, by the total population. Alright, so we can determine the frequency of white cats first. Alright, let me delete this. Okay, frequency of white cats is just equal to the number of individuals. It's stated in the problem, it's 160, divided by the total population, which is 1,000. So this is just equivalent to 0.16. Since the frequency of white cats is equal to 0.16, therefore q squared here is just equal to 0.16. because the white cats, the frequency of the white cats is the one with the homozygous recessive genotype, and that is denoted as q squared. So now we already have the value of q squared, so we can find or solve for the value of q. We just have to square root both sides of q squared equals 0.16. So we get the square root of that, and then we get the value of q, which is equal to 0.4. Alright, now we already have the value for q, and now we can use the Hardy-Weinberg equation, p plus q equals 1 to solve for p. Let me delete this. Okay, so the value for our q squared is 0.16, and then our q is 0.4. Alright, now to solve for the value of p, we just have to use the Hardy-Weinberg equation, which is p plus q equals 1. Therefore, p here is just 1 minus q, and then we plug in the value of q that we got here, which is equal to 0.4. So p is just 1 minus 0.4, therefore p is equal to 0.6. And now we have the values of p and q. We now have the allele frequencies in the population, and now we can solve for the remaining frequencies of individuals by using the formula p squared plus 2pq plus q squared equals 1. So our p here is 0.6. Alright, so we can find the value of p squared by just getting the square of p, which is 0.6. So 0.6 squared, so this is just equal to 0.36. Okay, let's just have, let's write all the values that we've solved here. P is equal to 0.6, p squared is equal to 0.36, 2pq is equal to 0.48. Okay, so p here is the frequency of the dominant alleles. Frequency of dominant alleles, and then q is the frequency of recessive alleles. Then p squared here is the frequency of individuals with dominant genotype, and q squared here is the frequency of individuals with recessive genotype. And then 2pq is the frequency of individuals with heterozygous genotype. Right, now we all have the frequencies of all individuals, or the allele frequencies of the population. All right, we can always you take note that we can always check the frequencies by substituting all the values back into the Heinberg or Hardy-Weinberg equations, which are the p plus q equals 1 and the p squared plus 2pq plus q squared equals 1. So let's do that. P plus Q equals 1. So we have 0.6 plus 0.4 equals 1. And then we have P squared plus 2PQ plus Q squared equals 1. So 0.36 plus 0.48 plus 0.16 equals 1. Now to get the number of individuals with the given genotype, black and white, we just have to multiply the frequency of individuals with P squared, 2PQ, and Q squared by the total population. So that would be P squared times total population, which is 1000 here. All right. So P squared is 0.36, so 0.36 times 1000. So that is just equal to 360. So 360 black cats of the BB, double big B genotype. And then for the big B and small b genotype, we just have to multiply 2PQ with 2PQ times the total population, that is 0.48 times 1000, which is 480 black cats of the big B and small b genotype. Okay, now we've already determined the frequency of the black cats. Because I mentioned earlier that black cats can have either the genotype BB, two big B's, and BB, one big B and small b genotype. And now we've already determined the values for the black cat's genotype. Now to solve for the white cat's genotype, we just have to multiply Q squared by the total population. So that is Q squared times total population. This is just 0.16 times 1000, which is 160 white cats, double B genotype, small b. If we're going to add them up, the white cats are genotype, BB genotype, and the black cats, which we previously solved, then that would be equivalent to the total population of 1000 cats. Let's solve another problem here. So we're given here figures of the dragons, and the wing trait is the one that is dominant. So we just have to solve for the frequencies. Q squared denoted as AA, then Q denoted as A, small a, P denoted as A, big A, and P squared as double A, double big A, and our 2PQ, which is just big A and small a. So we need to find the frequency of heterozygote dragons in the population. And again, we use the Hardy-Weinberg equations, which are p plus q equals 1, and p squared plus 2pq plus q squared equals 1. Alright, so let's count the number of the dragons given here for the total population. So the total population here is 21. Okay. So we have 21 dragons here. Okay, let's define the variables first. Q squared here is the frequency or the percentage of homozygous recessive, and Q is the frequency of the recessive allele in the population, and then P, which is denoted as big A, is the frequency of the dominant allele in the population. Then P squared, which is denoted as double big A, is the percentage or the frequency of homozygous dominant individuals. And then 2pq is the percentage or the frequencies of heterozygous individuals. Alright, so the total population here is 21, and then it says that the winged trait is the dominant allele. So let's count how many of the dragons are winged. So we have, so by counting from the figures here, we have 7 non-winged. Of course, that one will be a recessive. 7 non-winged recessive, and then the dominant or the winged trait is 14. This is the dominant. Homozygous dominant individuals. Alright, so we can now solve for the population of the individuals. So we can solve for the frequency or percentage of homozygous recessive individuals first, which is q squared. We can use 7 here. So 7 of 21 are homozygous recessive individuals. So that would be 7 over 21. So 7 of 21. This is just equal to 0.33. And this is our q squared or AA. Okay. The frequency of the homozygous recessive individuals. And now we can solve for Q. So Q is just the square root of 0.33, and that is equal to 0.58. Since we already have the value of Q, then now we can solve for the value of P, which is the dominant allele, the frequency of the dominant allele. So P is just equal to 1 minus Q. This is 1 minus 0.58. Therefore, P is equal to 0.42. P here is the big A. Alright, and then we can get or solve for the value of P squared. We just square the value of P, which is 0.42. This is squared, and this is just equal to 0.18. So this is double big A, which is the frequency of the homozygous dominant individuals. And now we can solve for the number of heterozygotes, which is 2pq. Okay, let's solve that. So 2pq is just equal to 2 times 0.42 times 0.58. Therefore, 2pq is just equal 0.4872, or we can round this off to approximately 0.48. Alright, and that's how to find the frequencies of individuals using the Hardy-Weinberg equilibrium equations, which are the p plus q equals 1 and the p squared plus 2pq plus q squared equals 1.